I want to talk about this first theorem here. It says that if f is path independent, it says f is path independent if and only if the line integral of f around all closed curves is equal to 0. So there's two things we need to show. The first thing we need to show is that f is path independent, that this implies that the line integral of f along all closed curves is equal to 0. And typically when we have a line integral over a closed curve, we put a little circle on the integral like that to let us know that we're integrating over a closed curve. Okay, so how can we think about this? Well, let's say this is an arbitrary closed curve. We just need to show that the line integral of f around this curve is equal to 0. So I'm going to call this point r of a, and I'm going to call this point here r of b. Okay, and we'll say it has counterclockwise orientation. So notice that we can split this path into two pieces. We have the path going from r of a to r of b. I'll call this C1. And then we have the path going from r of b to r of a. I'll call that C2. Now observe the following. The line integral of f over c is equal to the line integral of f over C1 plus the line integral of f over C2. Okay, that's C2. Now, this is equal to, so I'm just going to rewrite this first integral. This is equal to the line integral of f over C1 minus the line integral of f over minus C2. Okay, so what does this mean? Remember, these are line integrals of vector fields, so we have to give the curves orientation. So the orange curve, the overall curve, has counterclockwise orientation, so that gives an orientation of this direction on C1, and it gives an orientation of that direction on C2. So minus C2 is like the same path as C2, but just going in an opposite direction. Okay, and so the line integral of f over C2 is equal to minus the line integral of f over minus C2. We talked about this back when we talked about line integrals. Okay, but let's think about what minus C2 is. The curve minus C2 is going from r of a to r of b, but C1 is also going from r of a to r of b. C1 and minus C2 have the same starting and ending point, so the line integral of f over both paths is equal because f is path independent. So in other words, this integral here is equal to that integral by path independence. So in other words, their difference is equal to 0. Okay, and that shows that f is path independent. That shows that the line integral of f along a closed curve is equal to 0. Another way of thinking about this, I actually like the way of thinking about this because it involves a nice way to do estimates of integrals that you'll see doing math. So let's say C is a closed curve, and we're going to say f is a continuous vector function. So the absolute value of this is equal to, well, just what is, so this is going to be f, the absolute value of f dotted with r prime times dt. Remember, that's how we computed. Okay, but by the Cauchy-Schwarz inequality, this is less than the integral, this is going to be, say, t is equal to a to b. So by the Cauchy-Schwarz inequality, the dot product, f dotted with r, this is less than or equal to the magnitude of f times the magnitude of r prime of t dt. And now, since f is continuous, the magnitude of f is bounded by some overall constant on the curve. Let's say m. So this is less than or equal to m times t equals a to b, the magnitude of r prime of t dt. But this is just the length of the curve from t equals a to b. So this is equal to m times the length of the curve. Okay, so how can we use this to help us? Well, let's say we have some closed curve like this. Now, the line integral of f over that curve is equal to the line integral of f over this curve because f is path independent. Okay, and if we take smaller and smaller curves like this, the absolute value of the line integral of f over that curve is going to be less than or equal to some overall constant that doesn't depend on the curve times the length of the curve. But the length of the curve is going to 0, so it means that this is going to 0 as the length of the curve goes to 0. So what does this mean? It means the line integral of f over any curve that starts and ends at that point is going to be equal to 0. So that was that last argument was a good argument, but I think it might take you a little bit of time to follow. So just go back and listen to the argument again. But it is the type of argument that you'll start to make when you take more advanced math classes. And it's actually very natural. We're just saying as you integrate a function over a smaller and smaller curve, that integral goes to 0.